Hello everyone, my name is Luobin and this is my Workshop 3. Alright, so the primary goal for this workshop is to prove that dominant side program is NP complete program. So firstly, let's try to understand what dominant side is. Here is an example of the dominant side. Let's try to solve it first. We assume there is a graph G consists of a pair VE, where V is a non-empty finite side whose elements are called vertices, and E is a set of unordered pairs of distinct elements of V called edges. So here is a graph for this example. As you can see, I have included all vertices in set V and all edges in set E, which are 8 vertices and 14 edges. So as you can see from this graph, every white vertex is adjacent to at least one red vertex, which means that the red vertex dominates the white vertex. So to make this clear, you can see in the vertex B right here, change the color. The vertex B right here and the vertex C right here are adjacent to vertex A, right? And the vertex E and the vertex F and also the vertex H are adjacent to vertex J. So this means the vertex A dominates vertex C and B, and the vertex J dominates vertex C. Vertex J dominates vertex E, F, H. So the only vertex left is vertex D. So we are going to pull this one as an individual vertex into our dominating side. So therefore, for this problem, the dominant side will be AGD. Just make sure you cover every vertex when solving this kind of problem. All right. So after we had a basic understanding of this question, let's try to define the problem as a decision problem. So what is decision problem? The decision problem is basically a yes or no problem. So for this question, I have given a graph G, V, E, and an integer K. Does it have a dominating set of set K? So in the term of the input and output, we all know that an instance of the program is an input specific to the program. In this program, an instance will be a graph G, V, E, and an integer key. The output will be a dominant site. All right. So right now, let's try to prove NP completeness of this program. So to prove this program is NP complete program, we need to prove it is NP and also NP hard. So firstly, we are going to prove that the dominant site program is NP. So what is NP? The NP represents as non-deterministic polynomial. NP problem refers to a problem that can verify its solution in polynomial time. Another definition of an NP problem is that problem solution can be guessed in polynomial time. So how are we going to verify it? Before we're going to verify it, let's try to understand what is polynomial time. The polynomial time means it runs less than exponential time, which could represent as big O n to the power of c, where n is variable and c is constant. So basically, we can have big O n to the power of c or big O n times log n. Those will all be okay, but we cannot have big O constant to the power of n or factorials or big O n to the power of n. This is beyond exponential time, so this is not allowed. Back to verification. So how are we going to verify it? If any program is in NP, then given a certificate, which is an instance of the program and the solution to the program, then we will be able to check whether the solution given is correct or not. So obviously, this verification should be completed in polynomial time. in the term of a time complexity analysis. To complete the verification, we need to check every vertex in the graph is either in the sequence or adjacent to a vertex in sequence. In this case, the time complexity will be big O V plus E. So, which is pretty straightforward because we need to check every vertex and every edges, which means so the time gonna spend on that is going to be the V plus E. And because it can be done in polynomial time, this is polynomial time. So therefore, this problem is an NP problem. All right, so after we proved it is NP problem, we need to prove this problem is NP hard. So to prove this problem is NP hard, we need to show that a non-NP complete problem is reducible to a dominating set problem. Here I'm going to choose vertex cover, which is a non-NP complete problem. All right, so let's understand. Let's try to understand what vertex cover problem is. Same as the example I did on dominant side. Given an undirected graph GVE and a positive integer k, is there some subset of the vertices in graph G such that the subset size equals to 10 k, and every edge in J is adjacent to a vertex in the subset? Let's check the graph. Let me erase this first. Okay. All right, so basically what we are looking for is find the vertex that cover the most number of the edges. So therefore, for this graph, I will choose vertex C because, as you can see, it covers 3 edges. This one, and this one. So right now, the only one edge left in this graph is going to be this one. So therefore, we can either choose A or choose B. So basically, for this question, the solution will be C and B or C and A. Both will be okay. Just make sure to cover all edges in this graph when you deal with this kind of question. All right, so after we had a basic understanding of vertex cover and the dominant setting problem, you can see that the two problems looks quite similar, but there is actually a key difference. The vertex cover needs to cover each edge. Dominating side needs to cover each vertex. So it is different. All right, so how can we do the reduction from the vertex cover problem to the dominant side problem? Firstly, I will have the two exactly same graph. You can see I have same number of vertex and the same number of the edges. But you can see the difference is a key value, right? For the key value for the vertex cover is equals to 3, which means that the answer includes the 3 vertexes, 2, 5, 6. And the key value for the dominant side problem is equals to 2, which means there's 2 vertex in our solutions, which is 2 and 6. So how are we going to do the reduction? What we need to do right now is to make k for dominant side equals to 3. Therefore, we need to change the graph in some way. Just trying to make some change to the graph and make the k for the vertex cover equals to k for the dominant side. Makes them equals to each other. All right. All right, so here is the new graph I got. What I did is for every pair connected to the vertices, draw the third vertex and make a triangle. As you can see, let me use a blue color. You can see this. Oh, this is not blue. Oh, this triangle, right? This is triangle. This is triangle. I did this to the all vertex, to the all old vertex. So basically, I got another I got a new vertex and I I did it in the different color. You can see in the green color, the vertex V right here, right here, right here, right here. They all made a triangle with the old vertices. All right, so we have the new graph right here. So how are we going to find how are we going to do this? All right, let's try to find the dominating side in this graph by using a greedy heuristic. So how are we going to do it? Basically, we will start to find vertices that are adjacent to the most number of vertices. The way to do that is to stay with the greedy heuristic for the vertex cover problem, which is find the vertices that have the most number of edges. All right, so obviously every new vertex right here, they all only got 2 edges. So I can just pass it. I will start with the vertex number 6. So the vertex number 6 covered, let me see, 1, 2, 3, 4. It covered 4 edges. Vertex number 5 covers 4 also. And the vertex number 3 covered is 4. 4 is 4. And 2 is 1, 2, 3, 4, 5, 6. Number 2 covered 6 edges. And number 1 covered only 2 edges, same as the new vertex I got here. All right, so let's try to find the, okay, let's try to start with the vertex that cover the most number edges, which is number 2, all right? We will choose number 2, all right? After I choose number 2, I got this one passed, this one covered, I got this one covered, got this one covered, this one, and this one, 6 totally. All right, so the only vertex left is 2, 4, right? So it doesn't matter if we choose either of it, it will give me the same result. So therefore, I will going to choose the vertex number 5. All right, so the vertex number 5 covered this vertex, dominates this vertex, dominates this vertex. All right, so as you can see from this graph right now, we only got one vertex left, which is this one, right? Which is this one. So I will also select this one to our dominating site, right? All right. So right now, our solution is going to be the 2, 5 way, which is just make the k equals to 3. That's great. All right, let's continue. Okay, so before we continue, we need to figure out the time complexity during the reduction. It's pretty straightforward. We made a new graph by adding new edges and vertices. So same as before, it requires big OV plus E time. So therefore, the new graph can still be obtained in polynomial time, not a big change. Back to graph. All right, so we got k for dominant side equals to 3, right? We got this one and this one and this one right here. So this is a change I made to the graph I'm given for the for vertex cover problem, and I make the k for the vertex cover equals to k for dominant side. So what does that mean? That means we can now fit the new graph into a machine that solves the dominant side problem. And that solution will also be able to solve the vertex cover problem. Continue. So therefore, we can see that graph G1 means dominant side, the new graph. We can see that G1 contains a dominant side if and only if graph G contains a vertex cover. So this is important. You can only do this by using a graph contains vertex cover problem. So any instance of the dominant side problem now can be reduced to an instance of the vertex cover problem. All right, so this is proof that dominant side problem is NP hard. Right. in the conclusion, since we have proved that domain side program is NP and NP hard, therefore the domain side program is NP complete. We have everything, every requirement components we proved it. It is NP and it is NP hard, so it is NP complete. All right. So I think that's it. And here are my references. All right. Thank you.